Hope everybody's doing well. We're almost at the end. We only have a little bit more to go, and then you're done. And as I said, this is your last math class. You'll be very happy. You'll never have to do this again. Of course, the reality is statistics is sort of a math class, and Business 220 is sort of a math class, and marketing research technique is sort of math. There's math coming. It's mathy stuff. But this is sort of the end of the algebra, calculus direction that you have to go. And you're not going to use this that much in the sense of you're probably not going to be doing these calculations when the time comes. Well, some of you might really like this. But you really want to get the concepts. So that's what I keep trying to tackle. So unfortunately, we're not going to do that today. We're going to focus mostly on technique. But generally, you really want to know how exponentials behave, and how regular functions behave, regular mean polynomials, and what a derivative really tells you, what an integral really tells you. That's really what you need to get out of the course. Put that on camera, that's why I see this. That's really what you're trying to learn in business calculus. Because the truth is, most of what you will do mathematically will be involved with Excel, which can do an enormous number of things. But this is sort of the last topic to cover before the final. Next we're going to do review. So let's say tomorrow, I forget what time I set it for, but you will have a new paper homework, and you will have a new math lab. That are the last ones, so you don't have to do any more. Then when it's all done, I will drop the lowest homework and the lowest math lab. Okay? So if you have perfect scores in all your math labs up to now, feel free not to do the last one. Okay? So as a favor to all of you, we drop the lowest one. Okay? But it'll make you happy. Now we have to do a head count for a second. 4, 8, 10, 11, 35, 7, 1, 3, 45. There's 49 of you here. So we're going to do this bonus thing for you. So on your final exam, right on the cover of the final exam, 50. Merry Christmas. You will get 5 points added to your final exam. There are 50 of you. If 51 of you write that, none of you will get it. There. Got it? So you cannot tell your friends. That's their fault for not being here. Did you remember the magic phrase? Do I have to repeat that? There's 50 of you. If you write Merry Christmas, you'll get 5 points. If you don't write it, you don't get the 5 points. If I see 51 of those, I will count. None of you will get the points. Okay? Got it? Good. Last year's magic word was bananas, but people drew pictures of bananas. That got them 6 points instead of 5. But nothing else. All right. You should be rewarded for attending, as I was saying to these two guys here. You know, you're going to be in the business world. The worst habit to develop is not showing up for work. Okay? So there you go. So let's practice some more of these integrals. So this is the U substitution stuff. How about, ooh, this is a fun one. Let's start with this one. So you look at that, and what you do when you do the integral is you're looking for a function and you're looking for its derivative. And the function becomes u, and the derivative of the function becomes du. So you go to here and you say, well, the derivative of e to the x is e to the x. The 5 is irrelevant because 5 is just a constant, so you take the derivative of 5, you get 0. So you let u equal 5 plus e to the x. All right, that's long enough. So why don't we let u be 5 plus e to the x? How do I know I don't want to let u to just be e to the x? Well, first of all, if I did that, then this would just turn into u over 5 plus u, which wouldn't really help. Or one of them would be du, and that's not useful. You need to get rid of 5 also. So du is e to the x dx. Now we can substitute into the integral. We have e to the x dx, and we have 5 plus e to the x. So that's going to be du over u. The 5 plus e to the x is the u, and the e to the x times dx is the du. You can never have du in the denominator. Okay? So du always has to be in the numerator if you have a rational expression. So that's one clue. What's the integral of du over u? It's log u. Plus a constant, and then substitute back. You don't really need the absolute value bars because 5 plus e to the x is always positive. No, but e to the x is always positive. Yes, Jesse?
So anytime that there's a u in the denominator, we can automatically know that it's a log?
Yeah, if you have this form, it'll always be a
Yeah,
log.
it's a fraction u infinite was a log.
In fact, in general, if you see an integral with something over something, it's going to end up a log.
Okay.
Yeah. Be careful, not 100%. People are always looking for rules, and one of the problems with math is it's not always as simple as there's a rule, but a lot of time it is. Now, let's give you guys a couple of practice. Make sure you can do everything. We're going to do another flavor of this. So this one will violate your rule there, Jessica. That's not going to be a logarithm. Wonderful handwriting. This makes it a little better. Let's see. There you go. Here's some 3 entertaining ones. All right. So how do you do these? So as I said, you're looking for a function and its derivative, so you can rewrite the integral as one of 3 basic types. You kind of want it to either be a power integral, which we can integrate, a log integral, or e. So you want to turn whatever you've got into one of these 3 types. And then once it's turned into one of those 3 types, it's easy to integrate. So you use your substitution to get one of those 3 forms, and then you can substitute back. Remember, I put those up on Monday, but for those of you who weren't here. So you look at this one and you say, well, how do I know which one to do the substituting? Well, first, the derivative of x cubed is something x squared. So I'm going to want to go that way. The second is this is to the 5th. So if I can put this as u to the 5th, it would be easy to integrate. Or in this case, the minus 5th, but same thing. So let's let u equal 1 plus x cubed. The du is 3x squared dx. And 1/3 du, well actually we don't need 1/3, never mind. We've got 3x squared dx. So I can turn that into du. This will be u to the 5th. So I have du over u to the 5th, which is the same thing as u to the minus 5 du, which is the first type. Why do we use the letter u? Why not? Use any letter you want, it's just traditional to use u. So the integral of u to the minus 5 is u to the minus 4 over minus 4, which is minus 1 over 4 u to the fourth. And now substitute back. U is 1 plus x cubed, so it becomes minus 1 over 1 plus x cubed to the fourth times 4 plus a constant. So as I said, so what you're doing is you're using substitution to take a messy integral and turn it into something simple. Do the simple integration and then plug back in the messy part. How do you feel about that one? A little better. All right. So looks like I got the dx. So go here. So again, the derivative of something x squared is going to be something x. So let's let u be 1 plus 24 x squared. The du will be 48x dx. And you look at the integral, the integrand, they say, well, I have 12x dx, which is kind of like 48x dx. It's just off by 4. So 1/4 of du would be 12x dx. So I could rewrite this as 1/4 u to the 1/5 du. Why to the 1/5? Because it's the fifth root. So the 1 plus 24x squared becomes the u to the fifth root. And then the 12x becomes 1/4 du. I always recommend that you move the constant outside of an integral. It's easier to work with. Move it out of the integrand. That way, when you get messier integrals, it'll be less cluttered inside the part you actually do the integrating. All right, what's the integral of u to the 1/5? It's u to the 6/5. U to the 6/5 over 6/5, which is 5/24 u to the 6/5. And then substitute back. And you get 5 over 24, 1 plus 24x squared, to the 6/5 plus a constant. Remember that constant is very important. It looks like it's not important. You go, yeah, plus c. But you need that when you actually work with these things. Figure out what the constant is. Yes?
Why did you take a quarter of du?
Why I take a quarter of du? Because I look at the original integral, right? And if I want to do substituting, this could be the fifth root of u. This isn't quite du, because du is 48x. I only have 12x. So if I divide this by 4, then I get 12x, and then I can substitute. Okay? Anybody else?
Why is du 48x?
Why? Well, it's the derivative of this.
Okay.
So what we're really doing is we're saying du dx is 48x, and then we just move the dx over there. The du and the dx, you can think of as separate things. This was Leibniz thought of this. So calculus was simultaneously created by Newton and by Leibniz. Newton in England, Leibniz in Hesse, Germany. And this is his way of doing it, which turned out to be a better way, more efficient. Yes?
In the previous problem, what happened to the 3x squared?
Well, okay, so we took 3x squared dx, and we replaced it with du. So this becomes du. Okay? So what's going to happen is everything in the integral, the original integral, has to be replaced with things that are in terms of u. Can't have any x's left. Yes? I'd have to see what you're doing, but it's probably wrong. Okay? So, any to say
It's so confusing. I thought that in the middle way it's done, but when you started doing it, you were like doing a lot more than what I did. Like I stopped.
Well, I write out every step, but when you turn the integral, the goal is to turn it to something that looks like this, because that's a power, like the first one, and then you can integrate it, and then you can substitute back. But you don't want to substitute back until after you've done the integration, because the idea is to have an easy integral. Okay, let's do another one. let's let u equal the denominator, because it's a higher power. Du, well, what's the derivative of x squared plus x minus 1? Is 2x plus 1 dx.
So you wouldn't simplify it?
Well, how would you simplify that?
I was gonna try and factor the bottom.
Well, you
I
could,
didn't get to do this one yet.
right, if you try to factor the bottom, it doesn't really factor easily. You have to do quadratic formula. So you're not going to get anywhere with that. Right, obviously, when you have integrals, the first thing you should be looking to do is simplify before you do anything. Is the thing inside the integral in the simplest possible form? Generally, that's the way I'll give it to you. Maybe once in a while I'll cross you up, but not too much. I try to pick a bunch of these for you guys to practice with in my math lab. Plus, I will put up some stuff from my book on U substitution, which people find helpful, which I recommend working through. It's about 7 pages in my study guide. And that people say really helps them learn U substitution. So sure. Ignore the trigonometry ones, obviously. Okay, so notice this is from x equals 1 to x equals 4. But we're going to do substitutions for u. So first we're just going to ignore the limits of substitution and just take this integral and do the substitute. So x squared plus x minus 1 is u, and 2x plus 1 dx du. Okay, that integral is log of u. That's what that is u. No plus c, we don't need it. So this becomes the log of x squared plus x minus 1. And remember, it was a definite integral. So now we have to go from x equals 1 to x equals 4. So if you plug in, we get log of 16 and 19 minus log of 1. Log of 1 is 0. So this just equals log 19. Okay? How do we feel about these? Still a little confused? Okay, practice them some more. We're doing another type. Another substitution type. And we'll just keep practicing. If you guys are good at it, it's important. As I said in last class, and as I keep emphasizing, there's lots and lots of integrals that are quite difficult to do, or not possible at all. And the only way to do them is with approximations. Basically, the Riemann sum concept. There's some other techniques which you'll never get to in a class like this. And you cannot integrate them. They cannot be solved. So you have to, all you can do is numerical approximation. There's all sorts of stuff out there in the real world where you have an equation where there is no actual solution. So these approximation techniques are actually very important. And computers and calculators can do the approximation techniques to zillions of decimal places. You don't have to worry about how close you get. It's like pi. You can do pi to a trillion decimal places. It's not actually pi, but it's certainly more than you need to worry about. All right, what if I gave you something like this? Well, x times the square root of x plus 1 dx. I'm going to integrate that. So, well, here's my problem. If I let u equal x, that doesn't do anything. I'm just swapping u for x, right? This would be u, this would be u plus 1. I'm not any better off than before. If I let u equal x plus 1, the derivative of u the derivative of x plus 1 is not x, it's 1. So how are you going to do u substitution or something like this? Right? It doesn't make any sense, right? If I let u equal x plus 1, du is just 1 dx. So I can substitute for this could become du, and this would become the square root of u, but what about this? You say, well, another thing you could do is if u is x plus 1, then u minus 1 is x. You can rewrite this as now 1 times the square root of u, which is u to the half, du. So how do I know to do this trick? The power of x is the same. Remember I said when the power is one difference, then you're going to be able to do the derivative. So 24x squared, 12x. Derivative of x squared is x. But here, this is x and this is x, so the derivative of one doesn't give you the other. Now why would I do this substitution? It doesn't look like it's in much better shape. Well, now you can distribute the u to the half, and you get u to the 3/2 minus u to the 1/2 to u. You say, well, why did you distribute the x here? Well, then you would have gotten the square root of x cubed plus x squared, which doesn't help you in any way. So what you can do is you can rewrite the integral in a way where now it's easy to integrate. Because the integral of u to the 3/2 is u to the 5/2 over 5/2 minus u to the 3/2 over 3/2. That's the same as 2/5 u to the 5/2 minus 2/3 u to the 3/2. And then you just put x plus 1 back. So that becomes 2/5 x plus 1 to the 5/2 minus 2/3 x plus 1 to the 3/2 plus c. So let's do a couple of these until you get the hang of it. I was wondering who was the first person to think of this. The first time I saw an integral like that, I didn't know what to go through. Suppose I gave you wait. Don't pay attention to that. Can't do that. Okay. They give you something like that. So you say, well, let's let u equal x cubed plus 2. Let's try this trick. And u minus 2 would be x cubed. And du would be 3x squared dx. I say, okay, well, I can let this be u. But wait, I don't have an x cubed, and I don't have a 3x squared. But I do. Right? I have x cubed, x squared is x to the 5th. So I could let this, I could rewrite the integrand as that. So you take the x to the 5th and you break it up into x cubed and x squared. That's not fun. Wouldn't have thought of that. Okay, so square root of x cubed plus 2 becomes square root of u, which is u to the half. X cubed becomes u minus 2. And x squared dx becomes 1/3 du. Remember, the 1/3 on the outside. So again, this becomes square root of u. X cubed becomes u minus 2. X squared dx becomes the 1/3 du. It's a really tricky one. Now, distribute. And now it's relatively easy to integrate. In fact, it's the same integral as this one. U to the 3/2 minus u to the 1/2. We have 1/3 of 2/5 u to the 5/2 minus 2 times 2/3 times 4/3 u to the 3/2, which is 2/15 times x cubed plus 2 to the 5/2 minus 4/9 x cubed plus 2 to 3/2 plus c. So remember what I told you, simple looking integrals can turn out to be messy solutions, right? Let's go back into one of the slightly easier ones. All right, so let u equal x plus 3. So this will become u to the 5th. Du will just be dx, because derivative of u is 1, right? 1 dx. And then let u minus 3 equal x. So this then becomes the integral of u minus 3 times u to the 5th du. By the way, the other thing you could do is you could multiply this out to the 5th, distribute the x, and then you just have a big polynomial. Certainly valid. But if that was to the 50th, it would take you a while. So you want to have another technique just in case. Distribute the u to the 5th, you get u to the 6th minus 3u to the 5th du. And that is u to the 7th over 7 minus 3u to the 6th over 6. And substitute back. Got it? Okay, we're going to do some other stuff on Friday. See you Friday.